For the first time in the history of our species, we are looking at the face of a second moon of planet Earth. It is a gray, pitted rock no bigger than a building, and it has been quietly running alongside our planet for more than 100 years, unnoticed by almost everyone alive. A Chinese spacecraft just photographed it from 20 kilometers away, and the picture has reopened a question scientists thought they understood. Is this thing an ordinary asteroid, or is it a lost piece of our own moon, torn free in some ancient collision? The answer was supposed to get simpler as we got closer. Instead, it got stranger, and what happens next could rewrite the story of the Earth and the Moon. So before we begin, settle it in the comments. A piece of the moon, or just a stranger wearing its face? Subscribe so you're here the moment that capsule comes home and we finally know. Now let's get into it. Look at this image for a moment, because you are one of the first people alive to ever see it. A rugged gray mass, pitted and uneven, hanging alone against the pure black of space. It does not look like much. It could be almost any rock in the solar system. But it is not any rock. This is the first close-up photograph ever taken of a second moon of planet Earth, and until July of 2026, no human being had ever seen one of these objects up close in the entire history of our species. The object has a name, though it is not a name most people have ever heard. It is called 469219 Kamoʻoalewa. And what you are looking at was captured by a Chinese spacecraft called Tianwen-2 from a distance of only about 20 kilometers away. Think about that number for a second. 20 kilometers. That is closer than most people live to the nearest city. A machine built by human hands traveled for more than a year, crossed roughly 1 billion kilometers of empty space, and parked itself 20 kilometers from a rock that has been quietly shadowing our planet for longer than any of us have been alive, and it turned on its camera and sent this picture home. And here is the part that should stop you cold. For several years now, scientists have been arguing about one very specific question when it comes to this object. Not whether it is dangerous, not whether it will hit us. The question is far stranger than that. The question is whether this thing, this gray rock looping through space beside us, is actually a lost piece of our own moon. A fragment that was blasted off the lunar surface in some ancient collision, thrown into space, and left to drift alongside the Earth like a stone that fell out of a much larger stone. For years, that was just a hypothesis, a suggestion, an idea nobody could prove. And now, for the first time, a spacecraft is close enough to find out the truth. So let me tell you what this object actually is, because the story only gets stranger from here. Kamoʻoalewa is what astronomers call a quasi-moon or a quasi-satellite of the Earth. It is one of a small handful of objects that appear from where we are standing to circle our planet. And in the last few years, these objects have gone from being a curiosity to something scientists genuinely want to understand, because there may be far more to them than anyone assumed. This particular one is considered the most stable of them all. It has been keeping pace with Earth for at least 100 years, and it will most likely stay with us for at least a few more centuries after that. This is China's first ever attempt to fly to an asteroid, collect a physical piece of it, and bring that piece back to Earth. It is a genuine first for the country, and in a broader sense, a first for humanity, because we have almost never done anything like this with an object that sits this close to home. And the reason it matters so much is not just that we reached another rock. It is that this specific rock might be the single most important object of its kind we have ever been able to touch. Because if the samples that come back tell us this really is a piece of the moon, then everything we thought we knew about how the Earth and the moon exchange material and how violent our shared history has been is about to change. But before we get to what the sample might reveal, you need to understand something that sounds almost impossible when you first hear it. Earth does not have one companion in space. It has more than one, and almost nobody has ever been told about the others. Here is a fact that tends to short-circuit people's brains the first time they hear it. As of right now, the planet Earth officially has 8 quasi-moons. 8, not 1. And yet, if you stopped 100 people on the street and asked them how many moons the Earth has, every single one of them would say 1. And they would be right, and they would also be missing something extraordinary that is happening right over their heads. So let me clear up what a quasi-moon actually is, because the name is a little misleading. A quasi-moon is not a true moon. The moon you know, the bright disk that lights up the night sky and pulls the tides, is gravitationally bound to the Earth. It is locked to us. It orbits our planet, and it goes where we go because our gravity holds it in place. A quasi-moon does none of that. A quasi-moon is not held by Earth's gravity at all. It is held by the sun. It orbits the sun, just like Earth does, just like every planet does. It only looks like it is orbiting us because of a trick of perspective, and it is worth slowing down on that trick, because it is beautiful once it clicks. Kamoʻoalewa follows a path around the sun that is almost identical to the path the Earth follows. Almost, but not quite. Its orbit is just slightly different from ours, tilted a little, stretched a little. And because the two orbits are so close together, from our moving vantage point on Earth, the object appears to loop around us. It seems to circle the planet in this strange corkscrewing dance, drifting a little ahead of us, then a little behind, then swinging back around. But that loop is an illusion. It is the same illusion you get when you drive down a highway next to another car, going almost exactly your speed. The other car seems to hang beside your window, drifting slowly forward and back, when in reality, you are both just barreling down the road on your own separate paths. Kamoʻoalewa is that other car. It is not circling us. It is running alongside us around the sun, and the loop we see is just the two of us moving at nearly the same speed. That is why the name fits so perfectly. Kamoʻoalewa comes from an old Hawaiian chant, and it refers to an oscillating celestial object, something that wobbles and sways. Whoever chose that name understood exactly what this thing does. It sways beside us. It oscillates. It bobs along in our wake, like something caught in the current of a river we are both floating down. And it was discovered relatively recently, in the year 2016, by a survey telescope in Hawaii that was scanning the sky for exactly these kinds of faint, easily missed objects. And that word, faint, is the whole reason you have never heard of any of this. These quasi-moons are small, and they are dim, and they are genuinely difficult to see, even with good equipment. They do not blaze across the sky. They do not light up the night. They are gray specks moving against a field of countless other gray specks, and it takes dedicated searching to pick them out at all. So, they were not hidden from you. Nobody buried them. They were simply too quiet and too dark to notice until we built machines specifically designed to find the quiet, dark things. And it is worth understanding just how delicate these arrangements are, because it makes the object we are chasing even more special. Most of Earth's companions do not stay companions for long. They fall into these looping, Earth-matching paths, ride along with us for a stretch of time, and then the subtle tug of our gravity, or the pull of the sun, or a nudge from another planet, eventually knocks them loose and sends them wandering off again. Some of them trace what astronomers call horseshoe paths, drifting slowly toward Earth from one side, then reversing and sliding away before they ever get too close, tracing out a shape like a horseshoe over decades and centuries. They are more like passing acquaintances than true companions, visitors who linger for a while and then move on. This is the normal life of a quasi-moon. It is temporary. It is fleeting. It is the cosmic equivalent of a stranger who walks beside you for a few blocks and then turns down a different street, which is exactly why Kamoʻoalewa refuses to fit the pattern, and why scientists find it so compelling. It is not a passing acquaintance. It has planted itself in step with the Earth, and simply stayed, holding its position with a stubbornness the others do not share. And that unusual loyalty is one more thread pulling us back toward the central question. Why is this particular object so committed to our orbit? Is that stability just a coincidence of physics, or is it a clue about where it came from and what it is made of? Out of all 8 of them, Kamoʻoalewa stands apart, and this is the detail that makes it the perfect target. Most quasi-moons are temporary companions. They drift into this Earth-matching dance for a few decades, and then drift back out again, wandering off to become ordinary asteroids once more. But not this one. This one is stable. It has held its position beside us for over a century already, and the math says it will keep pace with Earth for hundreds of years to come. Of all the companions our planet has quietly accumulated, this is the one that has decided to stay. And that stability, that stubborn loyalty to our orbit, is part of what makes the next detail so hard to explain. Now that you know what Kamoʻoalewa is, let me tell you how big it is, because the answer is going to surprise you in the other direction. This object that has been shadowing our entire planet for a century is tiny. Astronomers estimate it measures somewhere between 15 and 100 meters across. That is it. At the small end, it is the size of a large house. At the large end, it is the size of a modest office building. You could walk the length of it in under a minute. The thing that has earned the title of Earth's most stable second moon would fit comfortably inside a city block, and it has been keeping perfect pace with a planet 12,000 kilometers wide. But its size is not even the strangest thing about it. The strangest thing is how fast it spins. Kamoʻoalewa completes one full rotation on its axis approximately every 28 minutes. Let that sink in. In the time it takes you to watch half of this video, this object will have spun completely around, not once, but potentially more than once. A day on Kamoʻoalewa, a single sunrise to sunrise, lasts less than half an hour. It is not tumbling gently through space. It is whirling, spinning fast enough that if you were standing on its surface, and if it were large enough to hold you down, which it is not, you would feel yourself being flung outward with every rotation. And you might reasonably ask how a rock ends up spinning that fast in the first place, and the answer is one of the quieter marvels of physics. Sunlight, it turns out, can spin an object up. When sunlight hits a small, oddly shaped rock and radiates back off as heat, it gives the object the tiniest possible push, a nudge so faint it is almost nothing. But space offers something Earth never does, which is time without limit and friction without end. Over millions of years, that feather-light pressure of sunlight, pushing a little harder on one side than the other because of the object's uneven shape, can gradually spin a small body faster and faster and faster, like an invisible hand flicking a top over and over across the ages. For a body only tens of meters across, that gentle solar torque is more than enough to wind it up to a rotation of once every 28 minutes. It is a reminder that in space, even sunlight is a force with consequences, and that the objects out there are shaped by pressures too subtle for us to ever feel. And that rapid spin is not just a fun fact. It is a genuine problem, and it is a genuine clue, and it is worth understanding both. The problem first. That 28-minute rotation makes this object extremely difficult to approach. Imagine trying to reach out and touch a specific point on a merry-go-round that never stops turning. Now imagine that merry-go-round is a rock the size of a building, floating in space, 1 billion kilometers from home, and you are trying to touch it with a spacecraft that costs enormous amounts of money and cannot afford a single mistake. The surface is constantly moving beneath any probe that tries to get close. This is one of the hardest kinds of targets you can possibly choose, and China chose it anyway, which tells you how badly they wanted what this object might be holding. Now the clue Because this is where it connects back to that haunting question of what Kamoʻoalewa actually is. When an object spins that fast, it tells you something important about what it is made of. A lot of asteroids are not solid rock at all. They are what scientists call rubble piles, loose collections of gravel and boulders, and dust held together by nothing more than their own weak gravity. And here is the thing about a rubble pile. If you spin it too fast, it flies apart. The pieces on the outside get thrown off into space because there is not enough gravity to hold them down. So an object that spins as fast as Kamoʻoalewa does and yet stays in one piece may not be a loose pile of gravel at all. It may be a single, solid, coherent chunk of rock. Something strong. Something that holds together under stress the way a real, monolithic stone would. And why does that matter? Because a solid, coherent chunk is exactly what you would expect if this object were not born as a typical asteroid, but was instead broken off from something much larger. Something like a moon. The fast spin does not prove the lunar theory, but it quietly keeps it alive. It whispers that this object might be a splinter, a fragment, a shard knocked loose from a bigger world, rather than a clump of debris that gathered itself together in the dark. So we have a tiny, fast-spinning, solid gray rock that has been pacing our planet for 100 years, and we have a question that will not go away. Where did it come from? And that question has a leading answer, an answer so dramatic that when you first hear it, it sounds almost too poetic to be true. For several years, the leading idea about Kamoʻoalewa has been genuinely astonishing. The suggestion is that this object is not an asteroid at all in the traditional sense. The suggestion is that it is a piece of the moon, a literal fragment of the same moon that hangs in our sky every night, somehow torn free and set loose to wander through space on its own, and eventually caught up in this Earth-matching orbit where it has been ever since. Now, where does an idea like that even come from? It did not come from imagination. It came from light. Specifically, it came from the way Kamoʻoalewa reflects sunlight. Every object in space has what you might think of as a fingerprint written in the light that bounces off it. When sunlight hits a surface and reflects back to our telescopes, different materials absorb and reflect different colors in different amounts. Rock made of one mineral reflects light one way. Rock made of another mineral reflects it another way. By carefully studying that reflected light, breaking it apart into its component colors, the way a prism splits white light into a rainbow, scientists can make an educated guess about what a distant object is actually made of without ever touching it. And when researchers did that with Kamoʻoalewa, they found something they did not expect. Its fingerprint did not look like a typical asteroid. Its fingerprint looked like the moon. More specifically, it looked like lunar soil, the fine, ground-up material that covers the moon's surface. And not just any lunar soil, but lunar soil that had been dramatically weathered, aged, and altered by long exposure to the harsh radiation of open space. The light coming off this little rock resembled the light coming off our own moon. And that single similarity cracked open one of the most intriguing possibilities in modern planetary science. Because if it looks like the moon, maybe it is the moon. Maybe, sometime in the distant past, something enormous slammed into the lunar surface. A meteor, an asteroid, some violent visitor, striking with enough force to blast chunks of the moon clean off into space. Most of that debris would have fallen back down, or drifted away, or been swept up by the Earth. But a few pieces, maybe just one piece, could have been thrown into an orbit around the Sun, so similar to Earth's own that it ended up as our companion. A survivor of an ancient impact, quietly circling beside the very planet whose night sky is dominated by its parent world. And scientists even have a suspect for where on the moon it might have come from. There is a crater on the moon called Giordano Bruno. It is a relatively fresh scar, as these things go, gouged out by an impact just a few million years ago, which in cosmic terms is practically yesterday. And crucially, the material around Giordano Bruno appears to reflect light in a way that resembles Kamoʻoalewa. So the story assembles itself almost too neatly. An impact a few million years ago carves out Giordano Bruno, flings a fragment into space, and that fragment becomes the wobbling gray companion we are only now flying out to meet. Add in the fact that its orbit sits so remarkably close to Earth's, closer than you would expect for a random asteroid that just wandered in from the belt, and the lunar theory started to feel less like a wild guess and more like the obvious answer. And that orbital detail deserves a second look, because it is stranger than it first appears. The vast majority of asteroids we know come from the main belt, a broad zone of rubble between Mars and Jupiter. And when one of those wanders inward toward us, it almost always arrives on an orbit that looks nothing like Earth's. Different tilt, different stretch, different speed. It stands out as a foreigner. But Kamoʻoalewa does not look like a foreigner. Its orbit is a close cousin of our own, so similar that it can maintain this looping companionship for centuries. And there are really only two ways to explain that. Either a main belt asteroid threaded an incredibly unlikely needle and settled into a near-perfect match with Earth by pure chance, or the object started out much closer to home in the first place, because it was born from the Earth-Moon system itself. When you put it that way, you can feel the pull of the lunar theory. A piece of the moon would already be on an Earth-like orbit, because it came from a body that shares our orbit. It would not have to thread any needle at all. It would simply be family. So the case built itself, piece by piece. A lunar-looking spectrum, a candidate crater with matching soil, a suspiciously familiar orbit, a fast spin hinting at a solid, broken-off chunk. Every clue seemed to point the same direction, back toward the moon, and that is what made this object such a quiet sensation among the people who study these things. For a while, that is where things stood. A tiny piece of the moon, hiding in plain sight, waiting for us to notice it. It was a beautiful story, and it was gaining believers. And then a very powerful telescope took a much closer look, and the beautiful story started to fall apart. This is the part of the story that almost nobody saw coming, and it is exactly the kind of twist that makes a mystery worth following. Because just as the piece of the moon theory was settling in, just as it was becoming the comfortable answer, newer and more precise data arrived, and it did not confirm the story. It complicated it. The new look came from the James Webb Space Telescope, the most powerful space telescope humanity has ever built, an instrument so sensitive it can read the light of objects at the very edge of what is detectable. And when that telescope turned its attention to the question of Kamoʻoalewa, the fingerprint it read was not quite the fingerprint everyone had been relying on. The earlier studies had suggested a strong lunar match, a surface that was distinctly red in the way weathered moon soil is red. But the newer data told a subtly different story. It suggested the surface might actually be less red and more neutral than scientists had previously believed. And that small shift changes everything. Because a less red, more neutral surface is not the signature of weathered lunar soil. It is the signature of something far more ordinary. It looks, in fact, like the fingerprint of a fairly common type of asteroid. The new data hinted that Kamoʻoalewa might be nothing more exotic than a typical stony asteroid, possibly what is called an L-chondrite, or an S-type, or an E-type body, the kinds of asteroids we find scattered all over that region of space. In other words, the newer measurements suggested that maybe this object is not a lost piece of the moon at all. Maybe it is just a rock. A common, unremarkable rock that happens to have an Earth-like orbit, and happens to have a surface reddened by extreme space weathering in a way that only superficially mimics the look of the moon. And that phrase, space weathering, is the villain of this whole confusion, so it is worth understanding what it does. Out in open space, with no atmosphere to protect it, the surface of any object is under constant bombardment. The solar wind, a stream of charged particles pouring off the sun, sandblasts it around the clock. Tiny micrometeorites, specks of dust moving at enormous speeds, strike it and melt microscopic patches of its surface. Over long enough stretches of time, this relentless weathering changes how a surface looks, darkening it and reddening it, altering the very fingerprint of light we rely on to identify it. So here's the trap. A weathered ordinary asteroid and genuine lunar soil can start to resemble each other because both have been reddened by the same brutal process. The similarity that seemed to shout moon might actually just be the shared signature of anything that has sat in space, unprotected, for ages. And the alternatives the new data points toward, the L chondrite, the S-type, the E-type, are among the most ordinary asteroids in existence, the plain gray stones that fill the space between the planets by the millions. If Kamoʻoalewa is one of those, then it is not a relic of the moon. It is a nobody. And that is the whole tension of this mystery, held in the space between two readings of the same light. One reading makes this object one of the most important rocks near Earth. The other makes it one of the most forgettable. And nothing we can see from a distance can tell us which reading is right. And do you see the trap that this sets? The single strongest piece of evidence for the lunar theory was the way this object reflects light. That was the whole foundation. That was the reason anyone ever thought this might be a fragment of the moon in the first place. And now that exact piece of evidence, the reflected light, the fingerprint, has become the most contested thing about it. One set of observations says the moon. Another set of observations says an ordinary asteroid. The very clue that launched the mystery is now the clue that deepens it. This is what I mean when I say the first images revealed something no one expected. People assumed that flying a spacecraft out to this object would settle the argument, that getting close would hand us a clean answer. But it has done the opposite. The closer we look, the more the two possibilities pull apart. On one side, you have a weathered spectrum, an Earth-hugging orbit, a fresh lunar crater as a birthplace, and a fast spin that hints at a solid, broken-off chunk, all pointing toward a piece of the moon. On the other side, you have newer, sharper data reading a neutral, ordinary surface that points toward a plain asteroid. Both cases are real. Both cases have evidence. And a photograph from 20 kilometers away, no matter how remarkable, cannot break the tie. So how do you break a tie like that? How do you settle an argument when the object itself keeps sending mixed signals? There is only one way. You stop looking at it from a distance. You reach out, you take a physical piece of it, and you bring that piece home to a laboratory. And that is exactly what Tianwen-2 was built to do. Here's where the mission goes from remarkable to genuinely audacious. Because collecting a sample from Kamoʻoalewa is nothing like scooping up a handful of dirt. Remember, this is a building-sized rock spinning once every 28 minutes, 1 billion kilometers from Earth. You do not simply land on something like that. You have to outthink it. And the plan that Chinese engineers came up with is one of the most ambitious sampling strategies anyone has ever attempted. But before any of that can happen, the spacecraft has to do the patient work first. The plan is for Tianwen-2 to spend at least 9 months simply orbiting the object, studying it, mapping its shape, measuring its spin, learning the geography of every ridge and hollow on its surface. 9 months of careful observation before it dares to touch anything. And that mapping phase matters enormously, because you cannot safely grab a piece of a spinning rock until you understand exactly how it moves. So for now, in these first months, the spacecraft is holding back, watching. And the better pictures, the truly detailed close-ups, are still a few months away from us, even as this story unfolds. And then, once the mapping is done, comes the daring part. Tianwen-2 is prepared to try not one, but 3 completely different methods of collecting a sample, escalating in difficulty. The first method is called touch and go. The spacecraft descends, briefly taps the surface, collects a puff of dust in that instant of contact, and immediately backs away. It is the gentlest approach, a quick kiss of the surface and a fast retreat. This is essentially the same technique used by earlier missions from other nations. An American spacecraft called OSIRIS-REx used a version of it to grab material from an asteroid named Bennu. And a Japanese mission called Hayabusa 2 used it to collect from an asteroid named Ryugu. So this first method has a track record. We know it can work. But even that gentle tap is far harder than it sounds. And the reason is gravity, or rather, the almost total lack of it. On an object this small, gravity is so feeble that it barely exists. A person standing on Kamoʻoalewa could jump and never come back down, drifting off into space from the force of a single hop. And when OSIRIS-REx touched Bennu, it discovered something that startled the engineers watching from Earth. The surface behaved less like solid ground and more like a pit of loose packing material. The spacecraft sank into it, and the asteroid threw up a spray of debris, as if the ground itself were barely holding together. That is the environment Tianwen-2 is flying into. A surface with almost no gravity to keep it in place, that may crumble or spray or shift the instant it is touched, on a body that is spinning the whole time. Every one of the 3 collection methods has to work in that unforgiving setting, where the normal rules of up and down and weight and footing simply do not apply. But Tianwen-2 does not stop there. The second method is hovering. Instead of just tapping and leaving, the spacecraft would hold its position just above the surface, hovering against that relentless spin, and extend a robotic arm to scoop up material while it floats in place. This is harder, because it means fighting to stay steady over a moving target for longer than a single touch. And then there is the third method, and this is the one that makes engineers hold their breath. The third method is anchoring and attachment. The spacecraft would physically attach itself to the asteroid, using a mechanism of claws and spikes to grip the surface and hold on, and then collect material not just from the surface, but from below it, digging in to pull up subsurface samples that have been shielded from space for who knows how long. Attaching a spacecraft to a rapidly spinning rock is one of the most difficult maneuvers ever seriously attempted in deep space. If it works, it would be a genuine milestone. And why go to all this trouble? Why risk 3 separate methods? Why build a machine that can grip and dig and cling to a spinning stone? Because of the question. Because a photograph could not settle whether this is a piece of the moon, but a physical sample can. Once you have actual grains of this object sitting in a laboratory on Earth, you can do something no telescope can ever do. You can analyze its isotopes, the precise atomic composition of its elements, and you can study its minerals grain by grain under the most powerful instruments we have. And lunar material carries a distinctive signature in its isotopes and its minerals, a chemical fingerprint far more reliable than reflected light. If the grains of Kamoʻoalewa match the known chemistry of the moon, the debate is over, and the answer is yes. If they match the chemistry of an ordinary chondrite asteroid, the debate is over, and the answer is no. Either way, the argument that has raged for years ends the moment those grains hit a laboratory bench. The tie finally breaks. But of course, there is a catch. Those grains have to actually make it back to Earth, and the journey home is its own kind of drama. Getting the sample is only half the challenge. The other half is the long road home, and it is a road with a very specific and very dramatic destination. According to the plan, if the collection succeeds, Tianwen-2 would depart from Kamoʻoalewa in April of 2027, carrying its precious cargo, and begin the long fall back toward the planet it came from. And then, in late 2027, as it flies past the Earth, it will do something clever. It will release a capsule. That capsule is the whole point of the mission. It would contain at least 100 grams of material, torn from the surface and subsurface of Earth's second moon. 100 grams. That does not sound like much. It is about the weight of a small handful of sand. But those 100 grams could be the most scientifically valuable handful of material we have collected in years, because locked inside them is the answer to the question. The capsule would separate from the spacecraft, plunge down through Earth's atmosphere as a streak of fire, and be recovered by Chinese scientists waiting on the ground. And in that moment, when they crack open that capsule and pull out the grains inside, humanity would finally hold in its hands a piece of the object that has been shadowing us for a century. And what happens next, inside the laboratory, is where the real magic lives. Those grains would be handled with almost unimaginable care, kept sealed away from Earth's air and moisture so that nothing contaminates the ancient chemistry locked inside them. Then, one by one, scientists would begin to interrogate them. They would measure the exact ratios of different forms of the same elements, the isotopes, which act like a birth certificate written into the atoms themselves. They would examine the minerals under microscopes powerful enough to resolve individual crystals, comparing them grain by grain against the samples we already have from the moon, the ones astronauts carried back decades ago, and the ones earlier robotic missions returned more recently. The moon has a chemistry all its own, a signature that ordinary asteroids simply do not share. So the comparison is almost brutally simple in principle. Either these grains carry the moon's chemical birth certificate, or they do not. There is no reddened surface to fool us anymore, no ambiguous reflection to argue over. Just the atoms, telling the truth. And think about what those grains could tell us. If the laboratory analysis comes back and says this is lunar material, that this really is a fragment of the moon, then the implications ripple outward in every direction. It would mean that we have, drifting right beside us, an actual piece of the moon that we could hold and study, a sample of the lunar surface that we did not have to fly all the way to the moon to collect. It would mean that the story of the ancient impact, the fragment flung from the Giordano Bruno crater, the survivor caught in Earth's orbit, is true. And it would tell us something profound about the history of our own neighborhood, about how violent the past of the Earth and the moon has really been, and about how material gets knocked loose from one world and scattered across space to end up near or even on others. That last point is bigger than it sounds, so let me pull on it for a moment. If a chunk of the moon can be blasted off and end up quietly orbiting the sun beside the Earth, then this is not a one-time fluke. It is a mechanism. It means worlds can seed their neighbors with their own debris. It means the material of the moon might be scattered in places we have never thought to look, and by the same logic, pieces of other worlds, maybe even pieces of Mars, or of the early Earth itself, could be drifting out there in orbits we have not yet charted. A confirmed lunar origin for this one small rock would turn every quasi-moon from a curiosity into a potential archive, a record of impacts and collisions written in stone and set adrift. And if the answer comes back the other way, if the grains say ordinary asteroid, plain chondrite, nothing lunar about it, then we close the book on one of the most tantalizing coincidences in the solar system, and we learn that space weathering can disguise a common rock so convincingly that it fooled some of the best instruments we have. That would be its own kind of important lesson, a warning about how easily reflected light can deceive us. But make no mistake about which answer would rewrite the textbooks. One of these outcomes is a shrug. The other one changes everything, and we will not know which until that capsule comes down. But here's something most people covering this story have completely overlooked. The mission does not actually end when that capsule hits the ground, because Tianwen-2 is not going to stop. It is going somewhere else entirely, somewhere even stranger. Done. After Tianwen-2 drops off its sample capsule during that late 2027 flyby of Earth, the spacecraft itself keeps going. It does not come home. It does not shut down. Instead, it uses the Earth's own gravity as a slingshot, whipping around our planet to fling itself out toward a second target, a completely different kind of object. And this is where the mission gets a science fiction quality to it. Because the next place Tianwen-2 is headed is one of the most bizarre objects in the entire solar system. Its name is 311P, and at first glance you would call it a comet, but it is not a normal comet, not by any stretch. When the Hubble Space Telescope observed this object, it saw something almost unbelievable. 311P had not one tail, not the single graceful streak we associate with comets, but as many as 6 separate comet-like tails, fanning out from the object like the spokes of a wheel. 6 tails. Astronomers had genuinely never seen anything quite like it. And the 6 tails were not there all at once by accident. They appear to represent 6 separate episodes, 6 distinct moments when the object shed a burst of material, each burst getting swept back by sunlight into its own streamer. So looking at 311P is a little like reading the pages of a diary. Each tale a record of a different day. The object lost a piece of itself. It is not a single event. It is a pattern of repeated shedding, a rock that keeps throwing off fragments again and again, leaving a fan of evidence trailing behind it. And that behavior tells us the object is not stable. It is in the slow process of coming undone, and we happened to catch it in the act. And what makes those tails so strange is the reason they exist. A normal comet grows a tail because it is made largely of ice, and as it swings close to the sun, that ice heats up and turns straight to gas, streaming off the comet and getting pushed back by sunlight into that classic glowing tail. But 311P is not behaving that way. Its tails do not appear to come from ice melting at all. They appear to come from the object physically flinging material off its own surface, because it is spinning so fast that it is essentially falling apart. As it whirls, it sheds streams of dust and debris from its surface, and the pressure of sunlight stretches those streams out into long, glowing tails. It is not a comet melting. It is a rock coming apart at the seams and throwing pieces of itself into space. And if that were not enough, observations back in 2018 hinted at something even more remarkable: the possibility that 311P has a small companion of its own, a tiny moon orbiting this crumbling, spinning, 6-tailed object. That would make it a binary, a pair, which would make the visit even more valuable. And there's a strange symmetry in that idea worth pausing on. We began this whole story with a moon that might be a piece of a larger world, Kamoʻoalewa, possibly broken off the moon. And now, at the far end of the same mission, we may find a crumbling rock that has spun off a little moon of its own. Objects shedding pieces, pieces becoming companions, companions raising the same question over and over. What exactly are these things, and how do they come apart and come together out there in the dark? The mission keeps asking that question in every place it goes. But we will have to be patient, because Tianwen-2 will not reach 311P until roughly January of 2035. When it finally arrives, it would settle into orbit and conduct a detailed study, scanning the surface, trying to understand exactly what is happening to this thing that behaves like both an asteroid and a comet at the same time. And that is not a random second stop. It connects directly back to the mystery we started with. Because both of these objects, the quiet gray companion of Earth and the wild, self-destructing 6-tailed wanderer, sit right on the blurry line between what we call an asteroid and what we call a comet. By studying both of them in one mission, scientists hope to find the boundary between these two kinds of objects, or maybe to discover that there is no hard boundary at all, just a continuum, a smooth spectrum of icy and rocky bodies that we have been forcing into two separate boxes. Kamoʻoalewa asks us what an object near Earth really is. 311P asks us the same question in a different key. and the answer to both may reshape how we categorize everything out there. So this single spacecraft is quietly carrying two of the biggest identity questions in the solar system on its back. But identity questions, especially ones involving a secret second moon and a foreign space mission, tend to attract a very particular kind of speculation. And it is worth confronting that speculation head on, because some of it sounds convincing until you look closely. Whenever a story has this many strange ingredients, a hidden second moon, a foreign superpower, a billion-kilometer journey, a rock that spins like a machine, the theories start to multiply. And I think you deserve to hear them taken seriously, and then you deserve to see what happens when you hold them up to the light. So let us go through them one by one, because the truth is more interesting than the conspiracy anyway. The first theory you will hear is that Earth has secret moons that we, the public, were never supposed to know about. That there is a hidden fleet of companions circling our planet, and someone has been keeping it quiet. And I understand why it feels that way, because most people genuinely have never heard of quasi-moons until today. But the reality is the exact opposite of a cover-up. These objects are cataloged openly the moment they are discovered. Kamoʻoalewa was announced publicly back in 2016, and it has been studied in the open by scientists around the world ever since. The reason you never heard about it is not secrecy. It is that it is a faint, tiny, gray speck that is genuinely hard to see. Nobody hid the second moon from you. It was just too dim to make the news until a spacecraft flew out to photograph it. The second theory is more pointed. It says that no country would spend all this money, all this effort, a journey of 1 billion kilometers, on just a rock, unless there was something secret involved. Hidden resources, a strategic advantage, something classified. And on the surface, that logic seems reasonable, because it is a staggering amount of effort. But look at what the mission actually earns, out in the open, and you do not need a hidden motive to explain it. This is the first time this country has ever returned a sample from an asteroid. The first time anyone has tried to anchor a spacecraft to a small spinning body like this. The first time they have run a long-term exploration of a deep space target beyond the moon. These are the kinds of firsts that only a handful of space agencies in all of human history have ever achieved. The prestige alone, the sheer scientific accomplishment, is motive enough, and the results will be published and shared, not locked away. Sometimes a nation flies 1 billion kilometers to a rock simply because reaching the rock is the achievement. The third theory is the boldest. It says that a fast-spinning object sitting in a suspiciously Earth-like orbit might not be natural at all, that it could be something built, something engineered, a probe parked beside our planet, disguised as a stone. And this is where the science becomes genuinely useful, because we can actually test that idea against what we observe. Everything about Kamoʻoalewa, its size, its spectrum, the way it reflects light, its rotation, is consistent with a completely natural rock. Its loop around the Earth, which might seem like deliberate station keeping, is that highway illusion we talked about earlier, a well-understood consequence of two objects sharing nearly the same orbit around the Sun. And here is the deeper problem with the artificial probe idea. It cannot be disproven, and that is precisely its weakness, not its strength. Any natural feature you point to can be waved away as good camouflage. A claim built so that no evidence could ever refute it is not a strong claim. It is an empty one. The rock behaves exactly like a rock, all the way down. And the fourth theory is the sneakiest, because it wears the costume of skepticism. It says that the piece of the moon conclusion is being quietly suppressed, hidden from us, because admitting the moon can shed dangerous debris toward Earth would frighten people. But think about what we have actually watched happen in this story. The lunar theory has not been buried. It has been argued loudly and openly in the scientific literature for years. And the challenge to it did not come from some authority silencing the truth. It came from newer, public data from the James Webb Space Telescope, released for anyone to examine, pushing back on the lunar idea in plain view. This is not suppression. This is science doing exactly what it is supposed to do, arguing with itself out in the open, following the evidence even when the evidence refuses to give a clean answer. The honest situation is not a hidden truth. It is a genuine, unresolved disagreement, and that is a far more exciting thing to witness than a cover-up. So strip away all four theories, and what are you left with? You are left with something better than any conspiracy. You are left with a real mystery, out in the open, that we are finally about to solve. A tiny gray rock, no bigger than a building, spinning once every 28 minutes, that has been quietly running alongside our planet for over 100 years, unnoticed by almost everyone alive. And right now, as we speak, in the middle of July of 2026, a spacecraft sits just 20 kilometers away from it, watching, waiting, preparing to reach out and take a piece of it home. In a few months, it will begin to map that surface in detail. In 2027, if all goes well, a capsule will fall through our sky carrying the answer. And when it lands, we will finally know whether the thing beside us is a lost fragment of our own moon or an ordinary stranger wearing the moon's face. Either way, something that has been hiding in plain sight for a century is about to be named. And if it turns out to be a piece of the moon, then the sky above you is no longer quite what you thought it was, because it means our moon has been leaving pieces of itself scattered around us all along, and we are only now, for the very first time, close enough to notice.